I'll hand over to you there.
Okay, Samuel, off you go. You can do the introduction and I'll come back on the case studies around data-driven decision-making and analysis.
Perfect. Thank you. Thank you, folks, for joining once again this webinar. So my name is Samuel Carvalho. I'm a researcher in tools and the IDM cluster. So we're going to talk today about some data-driven analysis and decision-making, and also some case studies. Okay, you have probably heard this before, that data is considered the new oil because it's really important, it's really valuable. And it's the core asset in Industry 4.0 and AI applications, which are like huge nowadays as well. And just like oil, it's not very useful if the data is just in its raw state, right? So we need a few processing steps to get something useful out of raw data, just like we need with oil. We need to process oil so it becomes like lubricants, it becomes fuel and stuff like that. So I'm going to talk a little bit today about the data lifecycle. So that's like a rough picture of what happens when we're dealing with data and data-driven analysis. So we have our facts, like the original data. When we capture it, it becomes information. It's a snapshot of a real process, a real object, whatever we're capturing there. From this information, we can gather some knowledge. And once we get knowledge, we can make informed decisions. Okay, so I'm going to go through each of these steps with you now. So starting with the data stage, at this point, the data is at its most raw stage, so it tends not to be so useful at this stage, right? So these are normally data related to process variables. So we would have like power, current, temperature, pressure, vibration, all these different like physical, properties of a given process, and it's in like the raw state. So for this stage, we need a data acquisition strategy, right? So we need to use the right sensors, the right signal conditioners. We need to transmit this data. We need to store this data. So this is where your hardware will kind of be like very close to your process. One key aspect when we are talking about capturing data is that the cost of capturing this information should be lower than the benefit it produces, right? So if you're spending like €1 per sensor, for example, but you're only getting like 10 cents of improvement on your costs, given the data that you get from the sensor, it doesn't make sense to use them. But what we see in practice nowadays is that acquiring and storing data is becoming so cheap that companies will just capture all they can. They will just censor everything. Some machines, they already come with data repositories inside them that you can just like query and get data from them. But there's still some considerations that we need to make when we need to balance like costs and the information, right? So how often, for example, you should sample a process for data. Because if you do it too often, you're using like unnecessary bandwidth, because you need, once again, to transmit this data, you need equipment to store this data. So you are basically wasting resources. But if you don't sample it often enough, so it's too rarely, you cannot get meaningful information from these data, or you can get misleading information. So this is a very typical case of not sampling as often as needed. So you can see here this helicopter that was like recorded by a camera, and it looks like it's not rotating, right? So the helicopter is kind of still flying. This is what we call aliasing, and basically that happens because the camera has a limited number of frames per second, so it becomes a video. So if you're not sampling your image often enough, or if your FPS is low, you will see stuff like this happening. So you are losing some information because you're not sampling the real thing often enough, right? How do I avoid this stuff? So there is a theoretical lower bound for it, is the Shannon-Nyquist theorem. that says that you should sample your process or sample whatever you're getting data from at least 2 times higher than your highest frequency, right? So in practice, we actually use a rule of thumb using 5 to 10 times the highest frequency. So for example, a quick example, if we were sampling sound, so we know that the human ear can listen from 20 to 20 kHz, right? So the theoretical lower bound for sampling audio, for example, if you want to, hear the same thing later, will be to sample sound at 40 kHz, right? So 40,000 times a second. If we apply this rule of thumb here, it should be at least 100 kHz, basically. Okay, so this is just like the theoretical lower bound and the rule of thumb that we normally use, which kind of it's just to be on the safer side. Okay, so the data was captured and now we are in the information stage, right? So the major concerns at this stage are how we store, how we manage, and how we access this information, okay? So now we would be talking about these relational databases, non-relational databases. If we're going to store it in the cloud server, it's in a local server storage. ERP systems, when you're talking about like manufacturing and stuff like that. And this is where, like if you're a software developer, where we normally implement the CRUD methods. So CRUD will be create, retrieve, update, and delete. So that's basically like the 4, let's say, key operations that you need to do with databases, right? You need to create new data, you need to get data from the database, you need to update whatever is there, and you need to delete data. So when you implement these 4 functions, you kind of have a fully functional database. And at this stage, we can also monitor and control processes based on the information that we get from this data. So we start getting these insights from trends, historians, dashboards. So this is where data visualization starts to get really important. So we can start seeing stuff like this, right? So this is like real-time information showing up in dashboards that we can get like quick insights from it. Now we jump into the knowledge stage, right? So when data becomes information, we can also extract knowledge from it. So this will happen when we can identify some patterns like correlations, trends, any like meaningful pattern that is showing up from the data that we can use to interpret some further stuff or extrapolate from this information. So this is where we are generating knowledge. So some examples of this stuff would be like modeling, prediction, inference, machine learning methods, optimization, digital twins. So every time you are extrapolating from your information to generate something new, okay? The knowledge that we get from this stage will directly feed the decision-making process, right? Which is the next stage. So here's just like a quick snapshot. I'm going to cover this specific case study at the end of the presentation, but we can start seeing stuff like this. So we can see like from my time series data, I can see like number of produced parts, production time, idle time. I can see like that my machine was idle for this time, then when it's green, it's producing. So we are modeling how a machine works, for example, and getting some extra information from it. Yeah, so the decision-making stage is the last one, and it's the final stage of the data lifecycle. And when we use the knowledge from the previous stage to perform informed actions, right? So just some examples here. This is not an exhaustive list. So you can use statistical process control. You can monitor overall equipment efficiency and some key performance indicators. And also you can optimize them at the stage because you can make decisions based on what you're seeing there and the knowledge that you have acquired. You can work on production scheduling. You can use predictive maintenance and compare efficiency between different machines. You can generate best practice targets, because now you know you have a knowledge of your process, so you know the best practice targets that you can achieve based on your knowledge from the data. One important aspect at this stage is that the right information should be presented to the right people at the right time, right, on the decision-making stage. So, for example, there's no point in showing real-time sales data to operators, or let's say average cycle time to the sales team, right? So they can do nothing about it. So people should be able to directly influence a metric that they have access to, or there's no point in just showing this to them. Okay, so for example, if the operator is working on the machine and he sees, let's say, for example, that the cycle time is getting longer and longer, the guy will probably say, okay, there's something wrong. I must, adjust something. Something could be about to break. So he can, act, make a decision, and change whatever is causing that metric to be different than it should be. Now, if this data, if this information is presented to, a manager or the sales team or somebody that doesn't have access to whatever is creating this metric, there's no much point in doing it. Okay. So now I'll just go through a quick example of this data lifecycle applied to an actual project, a case study that I've taken part. So this would be taking knowledge from energy consumption data. Okay. So I'm be talking specifically about CNC machines. So CNC machines, they use a lot of energy, right? Electricity. Basically because they have like loads of subsystems and they are like cutting metal, so that's a very energy consuming task. And if we analyze this energy consumption, we can actually generate some valuable knowledge about the production process itself. Okay, and then we can use this knowledge at the endpoint to help some decision-making process. So I'm going to cover all these different stages of the data life cycles on this specific project that I've worked. So in the data stage, when we need to capture data, right? So remember, this is the raw data. This is the raw stage of data. So you would have your electrical panel, and you put your sensors. So these would be like current sensors in your three phases feeding the machine. You save this data in a PLC, which is like a industrial computer, send it to a database, and then you can analyze this data. So this is how we get the data from the shop floor. Okay, and what information can we get from it? Each product that this machine makes creates kind of an energy fingerprint, right, for this product. So there are some like research already on everything that happens with these profiles, these energy profiles, and how to relate them to different stages of the production. So for example, we can see the machine starting, when it's ready for operation, when the spindle starts rotating, when the spindle accelerates. So we can see all these different spikes and kind of different levels on the energy usage that we can actually link to the product that we're making, right? So we can say that this is like an energy consumption fingerprint for every piece that the machine does. Okay, now to the knowledge stage. What can we get from it? If we monitor these machines for a long period, we start generating this time series data set, right? So if you monitor, for example, for a whole shift, so let's say the operator started working at like 10 a.m. and stopped for lunch at 1 p.m., right? So every spike like this one, like every little profile here is a piece being made, okay, by the operator. So we can see very clearly that he has been working from 10 a.m. to 1 p.m. Then we can actually have a further look in this information, in this data, and we can, for example, identify cycle times. So we can use some statistical methods. So in this case, just the autocorrelation. So we can identify like the most common cycle time of these parts being produced, right? So this is an important metric to monitor because One of the things that we know about CNC machines, for example, is that when the spindle or the head starts to get worn, it will take longer to do the same task, right? So this is something that we could monitor to, for example, use for predictive maintenance if you want. The other thing, we can start like engineering some features from this data and feed these features to machine learning models, for example, right? So if I know the cycle time, or I have a good guess about the cycle time, and I check, like, let's say, for example, one cycle time where one of these pieces was produced, I can get some statistical measures, and I can, change the dimensions. I can see it in a graphical way, in a different way, so I can get some more insights using machine learning models from this data. Now, once I feed this to my model, I can start seeing stuff like this that I mentioned before. So my model in this case was identifying production and idle periods, as well as counting the number of parts that were produced. And then from this information, I can extract even more insights, right? So this would be the output from my machine learning model. So you can see that it's identifying here that, this is idle, this is production, this is idle. So you can also count the number of produced parts. So we could try to, compare this against what's in the ERP system to see if it matches, to count how many scrap parts were produced and stuff like that. And then we get to the decision-making stage, right? So using all this knowledge that we have been acquiring since the beginning, we can have dashboards like this. So we can analyze the time that the machine spent in production and idle, the energy used in production and idle, and all because we know how many parts were produced. We know, the price for electricity. We know all these different things. We can get insights like this. So the machine spent 3.08 hours producing. 27 products were made during this time using this total of kilowatt hour. So in average, each product took this amount of kilowatt hour to be produced. The machine spent this amount of time in idle, and this is the amount of energy consumed while on idle. And if I include my cost, like the electricity cost here as well, I could break down the energy cost to every product, right? So I could say every product takes, let's say, €1 worth of energy to be done. And I can say also, if the machine is off, it's spending, I don't know, maybe 1 kilowatt hour. So not off when it's idle. So you could just turn it off and, save this amount of kilowatts, for example. So these would be an example of this complete life cycle that I was, showing to you here. And now I'm going to hand it over to John. John has some more interesting case studies that kind of follow the same life cycle, I'd say, but in some other different kind of sectors as well. Yep.
Thanks, Samuel. Can you hear me okay?
Yes.
Yeah.
So I was going to take on the point. We've worked with quite a few companies, particularly in the last 2 or 3 years, helping them with getting data and helping them to use that data to get added value. And in the end of the day, for the companies, the added value of digital transformation or the added value of digitalization is what's really important. You can jump on to the next one, Samuel. So the clear opportunity space we've been discussing for a few years. The graphic on the right comes from a 2018 report, and it shows the 3 waves where value is expected in industry across Europe. And we have seen clearly the automotive sector and logistics adopt robotics. You've seen videos of cars being assembled with production lines of robots with very few human touches. You've probably also seen the very large warehouses, the Amazon and logistics warehouses with many mobile robots moving parts around. So these are industries that were early adopters of advanced digital technologies, and they have seen significant value, and there are many case studies. We're probably somewhere, COVID maybe accelerated digitalization in some ways, but also delayed some projects happening. But the area of the mechanical engineering, machining of parts, discrete manufacturing, and plant engineering is probably where the value is being found today, where companies are moving from a low digitalization maturity to a higher levels and achieving savings and seeing the value proposition from that. You can see in electrical engineering, medtech sectors. The medtech is a little more difficult. And then when you get into the chemical and aerospace, the highly regulated industries, the opportunity isn't as great. So from the graphic, you can see that the biggest opportunity is in the discrete manufacturing, which is a huge sector across Europe. And it's really where we have seen the majority of projects we work on at the moment. So the benefits of improved digitalization, and we're often asked to kind of put some value on them, but firstly, the benefits are numerous. As Samuel talked about, the opportunity for data-driven decision-making is first and foremost and probably the most important. But having digital capabilities was very much shown with the onset of COVID. It allowed the companies who were more digitally mature, were more resilient, were more agile, were easier able to pivot to new ways of working. Digitalization, when it's done correctly, brings improved productivity, increased profits. The typical target areas very much for companies at the moment, and I'll talk about in our case studies, reduced waste, reduced scrap, improvements in yield, mitigating against failure modes, reducing maintenance, and so on, and reducing costs. A secondary benefit is often increasing production capacity. If your machines have less downtime because you have better monitoring, then you get more uptime and more production capacity. And some companies have moved into areas of developing new business models, looking at their sustainability, and using data to just be a better company. And that often has positive benefits in terms of attracting and retaining workers and talent. Thanks, Samuel. So as I said, I'm going to present a number of case studies across 5 different areas. And these are the areas that we find the most practical, useful, and added value opportunities with companies. So very briefly, around digital business tools, so removing paper, moving to dashboards and tablets for operators, what we consider lean improvements or operational excellence. Secondly, smart manufacturing is where we use the data from sensors, as Samuel suggested, or we add IoT devices, Internet of Things, or cyber physical systems to get data and to use and analyze that data better. And that's very good at providing predictive, for example, predictive maintenance or condition-based maintenance to improve operations. The area we see of quite a lot of interest for companies we're working with is around cognitive robotics and vision systems. So bringing more video and camera technologies to the factory floor provides a much richer data set. So the raw data from sensors like temperature, pressure, that's a two-dimensional data in some respects. When you put camera systems, vision systems, you get three-dimensional data that's far richer and provides much more opportunities for analysis. And then we work in the area of digital twins. And when you move to camera-based and virtual versions of your production line, you have opportunities to control your process through digital twins and to move to autonomous control in some particular types of factories. And the other key opportunity area for companies is using data to improve their sustainability, to improve their energy efficiency. So if you can identify where and when and how you're using energy, then you can find opportunities to minimize that, to treat it as a lean project to reduce the waste of electricity in a plant. And we have had many case studies with companies showing significant reductions of 20, 30 or 40% in their electricity bills through better data analysis of their energy consumption. Okay, so Samuel, you want to jump to the next one? So 3 examples. We worked with a company called Takumi, which are an SME, a precision engineering company, and with a technology supplier called Grattan Computing. Through that project, we added tablets to the shop floor to machines, CNC and milling machines, that allowed better visualization of the work that was being done and the pipeline of jobs that was coming. It also allowed direct digital transfer of the drawings for machining, so that the right part was always being made. But it also greatly improved the understanding from the data of the capacity available in the factory floor. And that capacity availability was available all the way through to the sales staff out in the field, out with customers, who could clearly see where there was opportunities in the production capacity to have parts made. Is a company that work on small batch sizes, very flexible and agile, and they were able to significantly increase the ratings for their major customer, from a sort of an average score to a very, very high score. And because of that, they have won significant business. They have nearly doubled their workforce from 60 to 120 over the last 2.5 years, and they credit their digitalization journey as being responsible for that. It improved their business methods considerably, and the trust that their customer has that they can deliver on time. Boston Scientific in Galway are a medtech company. A typical application in medtech is the quality of products are sampled. So a batch of products is made, some are taken aside and go to a lab, and after 2, maybe 3 days, the result comes back from the lab that some parameter is out of kilter, or some parameter is out of spec, and the work that was done last week has to be then found, brought back, and changed or scrapped. By moving to real-time data gathering within the production environment, and we've seen this in a number of occasions, there's a significant saving. Firstly, the effect of a failure is instantaneous. So if the parameter is seen to travel out of spec, the production can be stopped, it can be corrected, and you don't make product which you then later will scrap. So that's a very significant saving. But also these systems are often paper-based, and removing the paper, in this case, moving to a direct real-time system, reduced 12% for a team of engineers and manufacturing time that was spent just on moving paper around that part of the process, as well as an improvement in the speed of the production system to get product out the door. Stryker in Cork are a company who make hip implants in this particular plant from chromium steel. They're often machined, but in Stryker, they're very much at the cutting edge of using additive manufacturing to make the metal implants and the various parts that go with that. But one of their issues was essentially around the time and additive, and if you've seen the process of laying down layers in an additive manufacturing machine, it can take, particularly in hard metals, it can take numbers of hours to produce a single part. If at any point in that process there's a delay in the data transfer, that causes issues with the final build quality of the product. So through initially some data acquisition and analysis to understand the problem, that clearly identified the bandwidth of the system as causing quality issues down the field. And by tracing that back through the data, they were able to identify that and change it, and a very significant reduction in machine downtime, 60% reduction in machine downtime. You know, so and almost eliminating that particular type of fault or flaw in the product that would fail their quality process. Next one, Samuel. So those ones were based on you know, data sampling in some cases to give better results. Where we moved to getting data from sensors and using that and analyzing that data, we can find quite impressive results as well, but takes a little bit more investment. So in Henkel in Dublin, they make a glue. It's called Loctite. You may have heard of it. It's called cryonocrylate monomer synthesis. Is the scientific name. It's a very well established process. The plant has been running for over 30 years, and there have been many, you know, evolutions and changes, but the fundamental chemistry is still pretty much the same. Based on some tools and techniques learned with us, the researcher went back over nearly 10 years of SCADA-based data, so historical data that was sitting in the plant. And by correlating that data with various events and failures and issues and maintenance logs and a whole series of different types of information that was available, and using some quite advanced machine learning techniques, they were able to identify trends that they hadn't previously understood. They hadn't previously understood that trends in one area in the process led to problems in a different area. And by going back and identifying those kind of issues from the data, which was so huge, it couldn't be done by a human. You couldn't do this without the advanced data analytics technology. They got a 5% increase in the throughput of the plant. Now, that's a very significant improvement in a very mature process. And the number of process deviations dropped significantly. A plant very near us in Limerick here in Lufthansa Technics in Shannon, owned by Lufthansa Aero Group. They do repair on aircraft parts, and they use EDMs, electronic discharge machines, to rebuild or relayer the primarily aluminium parts. So by analyzing the tool wear, again using data analytics, using an IoT sensors and existing data from the machine, they were able to better predict the wear. So instead of replacing the tooling every week or at the start of every shift or every batch, they were able to monitor the actual tool wear and get a longer lifetime from the tools. That actually saved them from buying a second machine, a third EDM machine with a very, very significant investment. So they were able to double the capacity on the existing machines by having a real-time monitoring of the tool wear from a relatively straightforward data analysis application. Another company we work with, Zimmer, in make orthopedic parts similar to Stryker. In this case, they're made from grinding and shaping metal, so a subtractive manufacturing process rather than additive, and that's the more traditional approach. They'd be quite a large scale facility. So by putting data gathering, data acquisition systems onto existing grinding machines, which didn't have, you know, IT capabilities, they didn't have data available, and they didn't have all the data that you needed to understand the process. So by putting instrumentation onto the machines, they were able to get much more accurate reliability data, much more accurate data on what parts were being made at what point in time, and how the machine was, you know, what tools were being used, predicting what wear was going to happen on those tools. That very significantly reduced the downtime of the machines through better planned maintenance, a 40% reduction on the time recorded for maintenance work orders, a very significant reduction in unplanned maintenance outages. And one of their more significant things is when they started getting this data, so they first instrumented one machine, and now they've added the same facilities to 18 milling machines. They've started to see opportunities to rebalance the mix of products, so they can move production that was planned on a machine to a different machine. And that change means far less setup times in each month. We refer to that as campaign building. So instead of maybe having 18 different setups in a month and the machine running for a few days and then being down for a day while there's a new set of tooling and a new setup put in place, by balancing the best machines depending on what tooling is in place, they were able to reduce that significantly. So reducing from 18 to 5 setups in a month means gaining 13 additional production days on that machine. So that's a significant benefit from their data analytics. Thanks, Samuel. Okay, as I said, we work across robotics and vision systems. We're very much favorable towards this sort of technology. So we've had a very significant project for the last nearly 4 years with two companies, Cook Medical, who make medtech products, particularly stent delivery systems for keyhole surgery, and Vistamed, who are an SME, who make part of they're a supplier to Cook, so they make part of the delivery systems for the stents. They had an issue with, similar to the medtech, a sample-based approach to quality that might identify an issue in 2 or 3 weeks' time after a batch has been manufactured. And the problem with that is that involves a recall. That involves going back to take the product back from hospitals or to take it back from suppliers and to do an investigation at a very, very significant cost. And you couldn't be taking a week's production, aside from a plant to investigate what caused the issue or where was the deviation. By putting camera systems supporting the operator, we worked with them on a zero defect manufacturing process. So every step that's taken is logged. It's an AI-based assistant that supports the operator, giving them clear instructions on each step in the process, which allows less skilled operators to do much more complex assembly tasks. But it also provides a very accurate traceback facility. So if an issue is identified in 3 weeks' time in a hospital by a surgeon about to use one of the tools, you can trace now that batch back to the single hour and single operator that where maybe the issue occurred. And that has a very significant cost saving for the company. This has been built on 4 pilot lines now, with another one currently in development. We're going to keep going on time. We work with analog devices, so you're all familiar with cobots and collaborative robotics, and the main principle of operation is that they slow down dramatically when somebody comes close to them. So again, we had a data application to look at different sensor technologies that would allow the robot to work at higher speeds, but still safely, and to reduce that distance of safe working around the robot cell using new sensors, using time of flight 3D camera sensors. On the robotic side, we worked with Stryker again in Cork on their machining side on a robotics application. So they have a particular issue with an injection molding process. They were of the view that there was an operator issue that was causing a quality defect, and that the solution was to put robots on each of almost 40 machines for a particular part of the loading process. Through a data analytics exercise, looking at exactly what was happening, getting information from existing systems, in this case, existing machine data and sensors, using some quite straightforward data analytics tools from OSI Pi and from Microsoft Power BI. They were able to track back all of the OEE, the overall equipment effectiveness parameters, matching the issues that they had on the floor. So it was an exercise that took some months, quite a detailed piece of work. It could, again, you wouldn't really try to do this manually. It needed the data analytics and the data analytics tools, but it actually identified clearly the source of the problem, and it was not the operators. And so replacing the operators with the machines would have had no impact. And in the end, they shelved a very significant robotics investment that was no longer necessary, and a small fix on the machines and a control on the parameters, on thermal model parameters of the injection molding machine has resolved the problem. So, you know, it's that data-driven decision making that we're very keen to promote. Next one. So I'll jump quickly through these. So we're strong believers in digital twins and digital models as being a very useful design tool. It's a very good way to develop. We actually have a company locally. I mentioned Takumi already. They've developed a clean line. It's a plating line. It's adding coating to metal parts. It's one of the first in this region. It's been developed by an SME to supply some multinational companies in the medtech sector. That actually will be launched this Friday. The project has been in work for about 18 months. We helped them with a digital twin model of the plating line. And during that process, and the plating line was being built in parallel with simulation models on the digital twin, that identified bottlenecks, and through discussions with the engineers and the designers, a constant flow of small changes were made with an overall reduction of 20% in the cycle time that it's going to take to make parts on this new plating line. So that was quite an achievement that, you know, they wouldn't have done without the digital model to test different what if scenarios. And what if we change this? What if we move this loading gantry from one place to another? What if we change the flow of parts we bring in and where we bring them in? So, and the digital twin didn't just model the machine or the production line, but also the environment around it, the movement of the people, the stores, inventory and spare parts, all of that sort of that would impact on the operations of the production line. We just recently finished a project with Johnson & Johnson Vision Care, who make contact lenses, a very, very large plant in Ireland. But in Ireland, they also have a design group that are responsible for the development of new production lines in Johnson & Johnson worldwide. Through a digital simulation model, again, using a data-driven approach. So they sampled data for 6 months from existing production lines. They use that data to build a predictive model and a simulation model that would allow them to improve the design of future production lines. That approach has been shown to bring the production line, which can typically take 15 to 18 months from start or design to commissioning and installation, that it has reduced that time by 3 to 4 months. That's the equivalent of an extra 20 million in revenue per production line. So quite significant, and it allows for parallel validation and commissioning of parts and a lot of, again, what if discussions with the designers to happen before the plant is actually built, and then the expected uptime of the plant and the production line will be significantly better because the problems will have been solved prior to commissioning rather than in the 6 months or year after commissioning. And we have another project with a company called Glyn Technical Diamonds, looking at their the operation of their tooling. These are drilling tools using some advanced tooling, some advanced data analytics, thermal modeling, computational fluid dynamics around the performance. And we identified and worked with the company to develop a new product. So I'll jump on, Samuel. So in the last area, we've, as Samuel highlighted in his presentation, we've been working for a number of years on a framework for companies on energy efficiency, a data-driven approach to understanding their energy usage. We're just working at the moment with a company called Penn Engineering. They have about 700 employees, not quite an SME, but they were, and they're an Indigenous-owned plant, but their energy costs have increased 300% since 2020. As we all know, electricity costs have increased dramatically. in the last year and a half, but they have been really significantly expanding, increasing by over €1 million. And their production output has increased in that time, but not by the same factor by any means. So again, looking at some data-driven analysis, 4.7 million SCADA data point entries over the last couple of years. They were able to identify where their largest or most significant energy users were around the plant. And using a process we developed to identify what are the significant energy reduction opportunities. And they have drawn up a matrix of target areas to work on. The first one is on 4 washers that are on these, they're making metal parts, and there's a washing process that is run by electric washers. So within the first 4 months, they've identified a €40,000 saving just on better control and operation of those. And they've identified that through putting a camera in place to identify when parts need to be washed and when they come in and out of the process, and how it needs to be controlled more accurately. With Dupuy and Cork, again, a company who make orthopedic in parts. These are we probably work with each of those companies in Ireland. We did a very detailed analysis on using a lean methodology, value stream mapping to look at where energy was used in their production lines, and then identified savings of over €100,000 per quarter by improving their practice, better management, and better behavioral operations around the production line. The company have also used that investment of significant commitment to energy efficiency and have put a wind turbine up on site to part supply their electricity consumption as well. But the understanding of where they use energy came from a data sensorization and data-driven approach. With Cook last year, they saved 10% of their electricity year on year, comparing relative production figures, again through better data analysis and by adding some remote sensors to different machines and different parts to identify what's happening. And similarly, we did this with Takumi a couple of years ago. We reduced their weekend energy consumption by 50%, and they don't make any products at the weekend. But a lot of machines were left running or in idle, and there was significant waste of energy. We also, using a data and optimization approach, we looked at their compressed air usage across the plant and reduced that significantly, again avoiding an investment in a second compressor and avoiding quite a bit of downtime with the existing compressor. So by reducing leaks and waste and unnecessary usage, again identified through the data and the sensors that were added, giving that data-driven approach. Okay, I think that's for me, Samuel. Is there one more slide? So just to mention in passing that a number of these projects have been through a Masters in Digitalization, which is a research program we do with industry, and the industry champions themselves have led the projects. And we also deliver a program called a Certificate in Leadership in Digitalization and Manufacturing, which is often the starting point for companies to engage with us. And we can jump on from there. Samuel can hop on to the next one. That information will be shared with you after.
Yeah, that's it.
Yeah, okay. So that's it for me. So hopefully that was some interesting case studies and added value or value propositions for real companies in real projects. Have we any questions? Feel free to just open your mic, or we don't have too many people on the call. So do you want to stop sharing, Samuel? And if anyone wants to just pop on their camera and their mic, if you have a question for either of us.
You can put the questions on the chat as well if you want, guys.
Okay. I'll anticipate the first question. So we're often asked, how do companies get started? How do they start this journey? And we generally guide them towards a digital maturity assessment. So there are many tools out there. There's many, you know, for your industry, for your country. There's different tools available that allow you to, you know, put in a snapshot of where you are today, what sources of data you have in the company, what kind of issues that you have, and where you sort of want to go to, what sort of integrated systems or what kind of business objectives you have, and based on that analysis, and it could be something that takes 10 or 15 minutes to do. It might be something that is a little bit more, 2 to 3 hours, with some people in different roles in the company contributing to. You'll get back a report and some graphics and a snapshot showing where you are. But I think that companies have found that very helpful then to prioritize what type of digital projects or what type of data-driven projects they should start with. Yeah, Maria Jose.
Hello again. My question is, yes, I agree totally with you. The digital maturity of the assessment of the companies is very important. But I don't know if you know some way or some information that is already available about the maturity of the technologies associated with digitalization applied to certain sectors. Because in some cases, some technologies are very mature to apply to a certain type of industrial activity. But for instance, for textile industry, because we have some issues, for instance, robotics is very hard to apply in textiles due to flexibility of the fabrics. So do you know some place, or do you know something related with digitalization technologies applied to certain sectors? How is the maturity of them?
I suppose the short answer is no, I don't. I think there are a lot of digital maturity assessments, and they come from different industries. So, you know, I can think of one in the automotive sector that's quite focused on robotics and your suitability of your process for robotics. But robotics are more flexible now than you might think. We have one project in Thus where we're using a robot to make bread, with very soft grippers to actually knead, you know, to make the sourdough artisan bread in a bakery. So the technology of the grippers is increasing all of the time. We have just recently seen some maturity assessments for AI, which are about, is your industry suitable for different types of AI? So that probably goes more towards what you were interested in. I suppose the understanding of the manufacturing domain that you're in comes from the company in most cases that we deal with, and then is trying to find the right technology to fit with that. For example, with smaller companies, they're not going to have an SAP system. They're not going to have an ERP, enterprise resource planning solution, but there are software as a service options. There are much lower cost options to do that, but there is a lot of them available. So, and there's a lot of, and this is where I do think companies need to work with a local RPO or a technology center or a consultant or their European Digital Innovation Hub to identify what are the best technologies that might fit for their application. We do a deeper, so the typical maturity assessments take a few hours or a few days. We do a deeper assessment that takes a few weeks or a month with a company, and it's very much focused on the business metrics first. And how do you want to move your business metrics? Is it increased profit, throughput, more sustainability? And the focus on the metrics is what tells you what digital projects then are most suitable to try and work on improving that.
Can I add? It's just like actually complementary to what Maria asked there. You mentioned about the sensors, Samuel. Can you adapt those sensors maybe for the sector? Like, because I guess even textiles sector, they have the machines. Of course, they work differently. Maybe there's a person that is controlling the machine, but can you use the sensors even in those cases to kind of track when the machine is idle, how much is it spending in electricity, and kind of I know robotics and cobotics maybe is not as easy, but maybe the sensors or something like that.
Yeah.
How do you implement those sensors is something that it needs like to.
Yeah, I was actually having an interesting discussion about it with Frank last week, because we were like discussing if a vibration sensor would work with sound, and a sound sensor would work with vibration, because like both at the end of the day are like just vibration. Sound is vibration. But when we have scenarios where it's challenging to actually, plug a sensor to a process and stuff like that, what we are seeing nowadays is people using computer vision, which is kind of, it's, if you think about it, it's a type of sensor. And we had a lot of like nice developments in the last few on how we deal with the images that we capture. So like the deep learning stuff that we can, go through camera feeds and identify, even the project that John was mentioning with Cook Medical. It was a camera-based, looking at, hand-based, operator-based operations, assembly tasks, and still being able to identify, okay, this is step one, and step one is being, done the wrong way, so I won't allow it to progress to step two. So when it is challenging to just use traditional sensors, we normally use computer vision that gives us some more flexibility, and there are some good algorithms already done to work with the feed, basically.
There is also, getting the right tools depending on the size of the company. So for much smaller companies, for micro enterprises or SMEs, some of the IoT devices are quite cheap and quite straightforward, quite simple. They may not work for many years in your industry, but they might work for the next 6 months to give you insight into a particular step in a process. And the sensors and the board can be €50 to implement. And there is a number of projects we can help companies with that. There's one called Digital Manufacturing on a Shoestring. It's a UK-based project out of Cambridge, where they have quite a number of case studies and examples of how they've deployed very simple, low-cost sensor solutions, which can include cameras as well, on those fairly cheap Arduino or Raspberry Pi type boards. And that's been rolled into another project in the UK called the Smart Manufacturing Data Hub, where they will in time actually send out a box to your company with some sensors in it and a board and a connection to the cloud, and the data analytics will be there. So it's whatever your scale or size, there's a solution out there that's sort of the right size for that.
Yeah, and talking about size, like even the physical size of the equipment that we use nowadays, it has changed a lot in just a few years. So when we were doing that project that I was mentioning, that we were monitoring the CNC machines, our solution to get the data was like this huge cabinet with an actual computer and a PLC with some wheels that would, we would drive it and put it right beside the machine, clamp the lines, the power lines, and get the data. This would be saved in a database on the computer. We would go there once a week to get data, then work on the data. This was like 7 years ago. Now we just had like a kickoff meeting for a project last month, and the solution is a small box that has a SIM card, which is connected already to the cloud. So it's a sensor that already sends data to the cloud, so you can actually access the data from everywhere. It's very small. We can fit basically any machine very easily. And one big advantage that we normally don't think about it is that because it has its like own transmission capabilities, you know, its own SIM card and its own internet access. We don't need to go through the IT like people of the actual place that we're installing it, to go through firewalls, to go through, you know, all the regulations that you know, might be in place for their own ERP systems, because we are, you know, just getting raw data and sending it to the cloud and not even using their network. So things nowadays are much like this, you know, to get data, because there's a huge demand. So the market has, you know, developed a lot as well.
Did you another
Thank
question,
you.
Camilla, or do you wanna, is there anyone
No.
wanted to come in?
I think I'm just looking at the time here. If there's no more questions from the participants, we
Dave?
might just wrap up.
Yeah.
We have Dave there. Yeah, thank you.
Hey, how are you? Thanks for the presentation. It's quite informative. It's nice to see that we're actually on track and doing stuff right. We'd have quite a bit of that data analysis in already, and we kind of have the day-by-the-hour systems, and you're looking at your uptime states more than anything, you know, uptime, downtime, idle, and then that leads into CI opportunities. But I suppose what I'm trying to get at is I don't think we really look at the data, and you know, there are tools out there now to analyze data much better than a human being sitting in front. And for us to kind of go down that path, is there any kind of roadmap as to which software or data analytical tools you should be using for particular industries?
So there's a lot of different approaches. I mean, we used R in our studio as a maths tool. We often use Python coding to develop data analytics tools.
Yeah.
Samuel is more of an expert in the tools that are there, but it's more about customizing something to the type of data sets that you have, maybe than it is just plugging your data into any tool and it'll work perfectly, you know?
Yeah.
So it's that customization. Probably the end tool doesn't matter that much. They all have very strong data processing capabilities.
Yeah.
I don't know, Samuel, any thoughts on the tools?
Yeah, I tend to go with open source stuff just because like I come from the teaching side, so I'm normally teaching people how to use it. So it's like if you're teaching a tool that has a ticket, an entry ticket of 100,000 euros for a company, it's very unlikely that all of the people that you talk to will actually start using it.
Yeah.
But some of the big companies like Microsoft is already offering like some data analytics kind of off the shelf solutions. There's like Power BI and stuff like that, and they're just like adding new features every day. Even in Excel, if you look nowadays, they have loads of stuff already. So I'd say it would really depend on like your let's say long-term plans as well. Do you plan to start a whole department inside your company that will hire people to work exclusively with data, to develop new stuff? When you're willing to develop like very customized stuff, I'd say going with the open source like R, Python would be easier to work with. But if you want something just off the shelf that will fit your needs very quickly, I'd say you could have a look at the Power BI, Microsoft stuff already, because and it should like be plug and play with most databases and ERP systems. So
yeah.
And you can go to your local research center to get assistance with that.
Yeah, I think we'll have to. I mean, it's load the data there and none of us are really sure what to do with it.
Yeah, and in some of the examples that we had there, they already had data and they had been gathering data for 5 years or more, but there was still a lot of opportunity to mine that information and extract useful stuff from it. You know, like historical kind of understanding, but the resource was there, but not being tapped into.
Data hoarding.
Yeah.
But look,
Yeah. I suppose the end game would be to try and make quality decisions.
Yeah, and I think focusing on the business outcome first, because all of this is technology. It's just technology, and digital transformation really is about the business transformation using digital tools. So there are many projects that have been in the graveyard of technologies people bought in, or licenses they got for software, or robots they've put into factories that are actually not then in use a year later or 2 years later, and therefore wasted opportunity as well. So is there any other questions, or we might close the call at that if there isn't?
Thank you, Samuel. Thank you, John. I'm gonna send an email to everyone, okay, that joined or registered for the event with the recording and the material. So Samuel and John, if you can share the material with us. And if there's any other questions, if you want to get in contact with Samuel or John, you just send an email back to me, and we can just direct you to that, okay? Or if you have any other questions. So I think we can wrap up for today. Thank you, everyone, for joining. And
Thank you, folks.
Bye, everyone.
Have a good day.
Bye-bye. Thank you.
Bye-bye.
Bye.
Bye.
Bye. Thank you.